Hello everyone, in this tutorial I will show you how to build an Arduino polyphonic synthesizer and how to easily make Arduino play a soundtrack in the background. To this end, I will discuss the asmsynth library in version 0.1.0, which allows you to easily create music. The movie was divided into 4 parts: overview of the library, list of library functions, writing a sample program and configuration of the library. I apologize for any incorrect translation that may appear in the video. Let's start. The asmsynth library is a library that introduces a virtual synthesizer to Arduino for music generation. To increase performance, most of the library is written in assembly language, so this synthesizer is capable of generating up to 32 voices simultaneously. The disadvantage of writing this library in assembly language is that it is dedicated to the ATmega 328P AVR processor, or other 8-bit AVR architectures. It should also be remembered that this is only the first test version of the library. Only one selectable clock is required for the synthesizer to function. Do not use 0 clock as the Arduino library uses this clock, therefore on the Arduino Uno board avoid using pins 5 and 6 by PWM. The synthesizer can generate simple waves such as square, sawtooth or triangular waves. Most likely in newer versions of the library will also be added sine wave and noise. So much for general information about the library, but what does this library implement? Apart from executing an ordinary program, the library can also execute another program independently. However, the music program will have priority, and this program will continue to run until the delay instruction appears. The functions responsible for delaying the music program are delay_ms and delay_ci. The delay_ms function stops playing the music program for the time specified in milliseconds, and delay_ci stops the program for the selected number of counter interruptions. These functions will allow the processor to return to normal program execution during this time. After this time has elapsed, the processor will return to executing the music program and will continue to execute it until it is given another delay function, and so on. Do not nest these functions, it can affect all processor operation and cause errors that are hard to spot. It's a good idea to use a macro instead. After the entire music program has been performed, it will automatically go back to the beginning. The library adds virtual oscillators that generate sound. They are responsible for the sound synthesis. Every single oscillator equals 1 vote. The library allows you to calculate up to 32 oscillators, i.e. up to 32 voices, but the fewer votes there are, the less loaded the processor is, of course. With 15,625 Hz sampling and a 16 MHz processor speed, one oscillator uses an average of 2% of the processing power of the processor. Each oscillator can change the waveform frequency, volume, and phase if, for example, the wave needs to start all over again. The library automatically calculates all the oscillators and adds them together. This sum of waves is then converted into the corresponding PWM signals in the further part of the library. The settings and types of sound output will be discussed in the library configuration section. Of course, the oscillators can also be referenced from the main program, and you can even turn off the implementation of the music program. Doing so may reduce the CPU load, but the convenience of writing the program will decrease. This implementation scheme will also be similar in newer versions of the library. Please note that this is the first version of the library and therefore subsequent versions may be backward incompatible. This is what the list of all library functions looks like. You don't need to memorize them now, but if you need a feature it will be easy to find here. Some functions may not be available depending on the library settings used. Now that you know how the library works, you can start writing your program. This is an example program. And it does this. Now we will start writing a new program from scratch. It will play the Tetris theme. We will start our program by writing the main program. For example, it will be a simple LED blinking program. We check if everything compiles. Everything is fine. Now we include the library and add a synth setup function in void setup to configure the Arduino board to use this library. As you can see, an error popped up when trying to compile the program. This is because the library has been set to implement a second program that is not in the sketch. To fix this error, just add a second program using macros. Remember that the second program should have at least one delay. You should also remember not to use ordinary delay, as it is in the movie, but to use delay_ms or delay_ci. Also, be careful not to use these functions anywhere else than in the latter program. Now that we have the second program, we can take care of the sound generating process. For this purpose, we write macros responsible for the interrupt, and in them we define what oscillators are to be used and what wave shapes should be generated. The sequence of functions is crucial here. In order for the first oscillator to generate a square wave, write wave 01 and then what kind of wave should be generated. There are three types of waves: square, sawtooth, and triangle wave. We do the same with the next oscillators. For the Tetris theme, we need 2 square waves and 1 triangular wave. Everything is compiled without reservation so far. If we know that our delay will repeat, it is worth creating a macro that will make it easier for us to enter delays and allow us to easily change the pace globally. Do not create functions that use delay_ms or delay_ci, as this can make Arduino malfunction. These functions should be entered only in the macros of the second program. Everything still works. Of course, now I noticed that I entered the wrong function and that instead of the usual delay it should be delay_ms. It is also worth adding functions that reset the waves so that they start from the beginning of the phase. To do this, first turn down the wave, stop it, and then reset the phase. Similarly for the other waves. Note that the beginning of the triangular wave phase is shifted and starts at 25% of the int value. Now we come to writing the Tetris theme. By default, all waves are set to 0 volume, so you need to turn them up. You have to be careful that the square wave has twice the value as it is counted twice. The sum of the loudness of all waves simultaneously reproduced must not exceed the value of 255. Additionally, it is worth making a certain margin. It is not required, but if you hear distortions or crackles, it is worth turning down these waves a bit. Now you need to change the frequency of the wave. Can be used directly in the function to change the frequency of the letter name of the sound. For this purpose, we are also helped by functions such as a keyboard, which will automatically convert the key number to the appropriate frequency in hertz, which converts the frequency given in hertz. All the values entered in the video refer to the same pitch. Now complete the rest of the notes according to your notes. This is how the first part of Tetris looks like. Now we will try to have this fragment played twice. To save some space and not to write the same thing twice, we will use a while loop. We need a global variable for this, a local variable may not work. As you can see, everything still compiles flawlessly. Now I will add a second part. And this is how the second program looks like, recreating the Tetris motif. To configure the library, you should find the config.h file in the library folder. You can create a shortcut to this file to have easy access to it. This file should be opened with a text editor, e.g. Notepad. When opened, it will show three main groups of settings: main settings, output settings and additional settings. Below, there is also the manual mode which will be discussed later in the movie. We'll start with the main settings. As you can see, the first setting is polyphony. This setting defines the maximum number of voices that can be used simultaneously. Decreasing this value reduces the amount of memory reserved. 1 vote takes up 5 bytes, so 32 votes will take up as much as 160 bytes of memory. A maximum of 32 voices can be set. Unless a high sampling rate is set, then the maximum value is 16. Another setting is mode. This setting determines how the sound is emitted. There are 3 audio output modes. The first mode, i.e. the value 1, is the standard 1 PWM output. The second and third modes are designed to connect the H-bridge system. The second mode is 2 pins controlling the direction of the current and 1 PWM controlling the power of the current. The third mode is 2 PWM controlling the direction and power of the current. The last setting in the group of main settings is channel. This setting is responsible for whether the audio output is to be doubled or not. When the value is 1, it is unchanged, while when the value is 2, then the number of PWM and pins will double. Another group of settings are the input/output settings. This is where you define which pins and PWM are to be used. Everything is defined according to the order, e.g. when mode 1 and channel 1 are set, you only need to define PWM1, when mode 2 and channel 2 are set, you need to define PWM1, pin 2, and this is the first channel, and PWM2, pin 3, pin 4, and this there is a second channel. If mode 3 is defined and channel 2 should be defined PWM1, PWM2, first channel, PWM3, PWM4, second channel. Unused pins or PWM should be commented out so that they are not defined. The timer interrupt definition specifies which timer to use as the interrupt trigger. You can select 0, 1, and 2. If you are using the Arduino IDE or the Arduino library, do not use 0 clock. If you want to use a pin, PWM, or clock that is not supported by the library, or you are using another processor based on the AVR architecture, then you should use the extended library configuration below. The use is simple, you need to define the addresses of new pins or timers and that's it. To find out which address should be entered, check the processor's documentation which address corresponds to a given pin. All definitions related to a specific pin, PWM, or counter should be defined. Do not define the same thing in manual and normal mode. The pins must be set to the output in the sketch yourself, and the counters used should be manually set to non-inverting 8-bit fast PWM and, if necessary, they should also be synchronized. And that's it when it comes to pin configuration. The last group of settings are additional settings that extend the functionality of the library. Defining disable_volume will disable the ability to programmatically change the music volume, blocking access to the volume function. Defining disable_second program will disable the implementation of the second program. Defining enable_high sampling rate will increase the audio sampling rate. The default sampling frequency is 15,625 Hz. When you enable this function, it is 31,250 Hz. Enabling this option will reduce the number of polyphonic voices to 16. Defining enable_motor will allow motor control. This will unlock the use of the motor A function, and if channel 2 is defined, motor B. Specifying enable_ADC will enable automatic ADC reading to change the music volume. This will unlock access to the AD channel function, which will allow you to change the ADC channel. That's all this library offers. Subscribe to this channel to not miss new videos using this library. You can comment on what can be extended or what can be improved in this library. I am learning to program, so such comments will also be helpful. See you soon.